We're going to take some time to work through another virtual lab. This lab is the enthalpy of reaction in Hess's law, and in this lab you're going to be running some experiments and calculating the heat of reaction for those experiments, and then using Hess's law of summation in this lab as well. So this lab is a little bit more tedious in terms of calculations, so I'm going to have a few videos for you to work through, and we're going to take this lab in steps. And seniors, you'll be happy to know that this will be your final grade for fourth quarter, because this will take us into next week, and then you'll have some time to finish out writing the lab report and getting that submitted by the 22nd. So seniors, this is it for you guys. And then juniors will be working on something for those final 6 days after we get through this lab. So what I would ask you to do is make sure that you have the lab either printed out or somewhere that you can reference it while I'm going through this pre-lab section of the lab handout. Also, I want to make sure that you know on the class page is the lab report write-up instructions. So you want to make sure you're looking at that too, because it is a normal lab write-up, nothing formal about it. It would be like what you would write in your lab notebook. So I just want you to take a look through that, so if you have questions you can ask. I can't stress enough to take some time to read the background section of the lab. It helps with the understanding of what we're going to be doing during the lab and why we're going to do it. And it actually will give you an indication of how a scientist would use Hess's law in real life. So in this lab, 3 separate reactions are going to be performed. I'm going to give you a brief overview of those reactions now, but also show you what you would have done in lab to run those 3 reactions. So that will be in another video, but today we're just going to talk about the 3 reactions. So the first reaction that you would be running would be a reaction between sodium hydroxide and hydrochloric acid, and this should look familiar. It's a neutralization reaction, so you know you're going to form a salt and water. The next reaction is going to be with ammonium chloride and sodium hydroxide. And the third reaction is going to be with ammonia and hydrochloric acid. So we're going to be looking at these 3 reactions and performing these 3 reactions. And the enthalpies of the first 2 reactions, so reactions 1 and 2, we're going to calculate the delta H's of those with the data that we collect, and we're going to use that to determine the delta H of the third reaction, which is ammonia plus HCl. We are also going to calculate the delta H of this reaction. So we're going to calculate it, and we're going to have an experimental delta H, but we're also going to calculate it from experiment 1 and 2. And then we'll be able to compare the theoretical and the experimental at the end and do a percent error. And I will get into all that. That probably sounds a little bit confusing right now. Maybe not the best explanation to get into right now, but it is what you're going to be doing in post-lab calculations and later calculations in this lab. So it's coming up, and it will make more sense then. So in these 3 acid-base reactions that we're going to be running, like I said, the first 2 reactions, when added together, should equal the third reaction, and we're going to test that. We're going to be using a coffee cup calorimeter, which you're all familiar with, a styrofoam cup, a thermometer, and running the reactions in that coffee cup calorimeter. It's going to be used to determine that temperature change, and then we're going to use that to calculate the heat, or Q, and also the enthalpy, or delta H. So, and also then that last bullet point, we're going to use the third reaction to compare values calculated with measured values, and I'll get into that in the post-lab analysis. So you don't really need to worry too much about that. That's just to give you a heads up about what's coming up next. So today's focus is going to be on the pre-lab questions, which I'm going to guide you through the work. I'm not going to give you the answers because I do want you to work on them and try them and see how you do. So I am going to kind of give you some hints along the way, and you'll submit these pre-lab questions. I'm going to look them over. I'm going to send them back to you. Again, I'm grading for completion, so you need to try the pre-lab questions. But I am going to go through them, and if answers are incorrect, I'm going to fix them. So you want to make sure you check the feedback that I send back to you, because even if you get a 5 out of 5 or an 8 out of 8, depending on how I score these, it doesn't mean that you've gotten everything correct, because I'm only checking for completion. So just be mindful of that. So I don't have 1 and 2 up here because they're definitions. I think that you can all look up a definition in the background or in your notes from previous videos, and you can write a definition. So I'm going to start with number 3, because number 3 is math. And so I want to give you a little bit of background to get you started on the math. Now, I like to go through and see what I'm given and kind of highlight those things, and then try to figure out what I'm determining. So in number 3, it's giving me the specific heat of the solution. So it's telling me that basically it's mostly water solution if I'm using 4.184. So that's important. It's also giving me the density. So that might be important. And then it's telling me solution A is going to combine with solution B, and I'm using 25 mils of each. And it's giving me the initial temperature of 21.4, and it's also giving me a final temperature of 25.3, and it's telling me to calculate the heat of reaction. And it's also saying there's no heat loss to, and that's a typo. I didn't type this, Flint Scientific did, but that should be calorimeter, not colorimeter. And then it's also saying be mindful of your sig figs. So we're assuming no heat loss to the calorimeter. That's something that we've always assumed so far. But in reality, there is a little bit of heat loss to a calorimeter. So when we actually run this experiment, we are going to calculate the heat capacity of the calorimeter, meaning how much heat did the calorimeter take on, and we're going to calculate that and then use that in our calculations. But this one's saying assume there's no heat loss. So basically you're calculating Q, and if you remember, when we calculate Q, Q just equals the mass times the specific heat and in this case the specific heat would be of water because our solutions are mostly water, and then we're going to multiply it by delta T. And we have most of that information. Now, there's one thing that you need to be mindful of. This is an exothermic reaction. So that means that our Q value should be negative because the reaction is giving off heat. So when we calculate Q, it's actually going to be a negative value for Q. So when you solve, this should be negative for your answer. Now, a couple things. You can calculate delta T because you're given that information up here. So you're going to take 25.3 and subtract 21.4 and plug that in. Now, one thing that's different in this problem that we didn't really do before, we always assumed the density was just 1, but they're telling us the density is 1.02. So we need to actually determine the mass used on that density, or used with that density. So to calculate the mass, you have 25 mils plus 25 mils. And so that means you have a total of 50 mils. And you need to convert that using density to grams. So you want to go to grams using density. And I'll let you work that out. Now they're giving you a density of 1.02. So that means that 50 is going to be a little bit off. You can't just say it's going to be 50 grams because it's not just 1, it's 1.02. So you need to do that calculation and then plug that in for mass. They give you the C sub P. I generally like to use 4.184, but since your lab is telling you 4.18, you can use that as well. It doesn't matter to me. It's out in that thousandth place, so it's not going to affect the calculations too much. So you're going to plug all of that information in and solve for your Q. So that's number 3, so I'll let you work on that one. So now if we take a look at number 4, the question's telling us to take into account the heat loss to the calorimeter and determine Q. So if you look in the background section, it gives you the information to calculate the Q of reaction, and so I'm going to write that out for you. And it says that the Q of the reaction equals a negative Q of the cal, or calorimeter, and we're going to add that to whatever we calculated for Q of the solution. And we're going to use that calculation to determine the Q of the reaction. So in this case, we're taking into account that heat loss to the calorimeter. Something I want to kind of hint around at is that the Q of the cal, when we calculate that, is going to be given to you in joules per degree C. And the Q of the solution, which we calculated above, is just in joules. So the Q of the cal must be multiplied by delta T to cancel out the degree C so that you can add the Q of the cal and the Q of the solution together. Otherwise, you can't add them together because the units are not the same. So we have to do one little extra step there, which I'm going to show you right now. So in the problem, they give you the Q of the calorimeter, and that's where you have to multiply by the delta T that was given to you in question 3 to get rid of the degree C. So that's the first thing that you need to do. And then once you calculate, do that calculation, you can plug in that number because now it's in joules, and you have joules plus joules, and you can calculate the heat of reaction. Again, you want to make sure that your Q, your final Q, is negative because the reaction is exothermic, giving off heat. So the Q of reaction you always want to make sure is negative there since it's endothermic. So another type of reaction that we actually talked a teeny bit about when we calculated delta H is knowing that delta H is measured in kilojoules per mole. And let me write this out so visually you can see what I'm saying. And delta H, when we usually look at that, it's kilojoules per mole. Now you calculated your Q in joules, so you're going to need to convert the joules of Q to kilojoules. And then you also have to make sure that you calculate the number of moles that you have so that you have your delta H of reaction in kilojoules per mole. Okay, that's how that delta H is measured. So that's just a little bit of background. So this question is asking you to determine the delta H of reaction using the Q that you calculated in number 4, which we just went over. Remember, it's a negative value that's in joules. And now let's look at the reaction that is given here. It's saying A plus B yields AB. We have coefficients of 1 for everything. So what that's telling me is that my moles of A equal my moles of B, which equal my moles of AB. So that's what that is telling me. All the coefficients are 1, so all the coefficients are equal. Now, I was given 25 milliliters of A. This is telling me that the molarity of that is 0.60 molar. We know that molarity is moles per liter. So we can take that 25 mils as our given and convert it to liters. So you have to convert this to liters before you can use it. And then just multiply it by the molarity. That's going to give us the moles. If I calculate it for A, that means that the moles are equal in B. So whatever I calculate for A is going to be equal for B and also equal for AB. So if I want to calculate the delta H of reaction, let me move over to this little corner. The delta H of reaction for this reaction is going to be my Q value divided by the moles of AB, which is what we just calculated here. Okay. The Q of reaction, you just have to make sure that you're converting that to kilojoules so that you can plug that in and you make sure that you get that in kilojoules per mole. So that would be how you would get your delta H of reaction in kilojoules per mole. Hope that makes sense. Again, if you have any questions, please make sure you reach out and ask. You can either ask in the forum that's set up for you, or you can just send me an email. The forum is helpful because then others can look there to see if that question was asked. But emailing me is fine too because it's easy. I'm always on my computer, so I'll get back to you pretty quickly. So again, you want to make sure that you're doing the Prelab, and you want to get that in so I can double check your math work and make sure you're on the right track, because you'll be using these calculations in your post-lab analysis after you watch the video that shows you the procedure for this experiment. And as always, I like to tell you what your assignment is on the last slide. You're completing those pre-lab questions number 1 through 5. Submit to the Dropbox. Please handwrite your answers. You can submit it as a picture or PDF just like always, and it's due on Tuesday, May 12th, again in the Dropbox. I'll be checking them and sending you feedback, so please make sure you check your feedback, because full points on the assignment doesn't mean that you got everything correct, as I mentioned before. Hope you guys are doing well. Have a great day, and I'll see you in the next video.